I'm hitting record. We're just gonna go, man. We're just gonna go.
Right now.
All right, ready? Look at me. And 3, 2, 1. I clapped. I clapped behind the mic. Okay.
3, 2,
1. All right. This is it, baby. We're in. All right. Welcome those viewing, listening, experiencing. We've probably had about 2 hours of technical difficulties, and we're excited to bring you a podcast today. My name is DJ, and this is my co-host, Bruno. So we had a topic in mind, and I don't want to go with it anymore. I bring abstract, I bring thoughts, Bruno brings details, but instead, actually, Bruno, run away, lead us somewhere beautiful. in your choice of, I believe you wanted to talk about genetic engineering, or what you're working on currently with your PhD now that you no longer have non-disclosure agreements.
Yeah, I mean, to disclose, I'm not allowed to talk too much about intricate details of what I'm doing, but I can talk about, but the intricate details is going to be really boring anyway. But yeah, so I'm a PhD candidate here in Vancouver, and I'm entering my third year of my PhD, so I'm kind of within like the middle age of my PhD journey. And yeah, what I'm working on really involves a lot of genetic engineering, a lot of what people call CRISPR. It's a bit of a hot topic. And yeah, we can kind of explore that. So I guess the long short of what I'm doing, not to bore too many people, it's not a science podcast, but is I am doing a lot of work with therapies for type 1 diabetes. Specifically, what I'm looking at is trying to improve the current method to treat type 1 diabetes. I mean, we all know that traditionally people take insulin when they're type 1 diabetic. Insulin's required to regulate blood sugar. And the problem with just taking insulin is that, first of all, around 30% of people who use insulin, they don't really respond very well to the treatment. They still have very dysregulated blood sugar, and we all know that chronic high blood sugar or having long sweeps of high blood sugar and low blood sugar is very detrimental to health.
Wait, why?
Well, think about it this way. So your body wants to be at homeostasis, right? So if we define homeostasis, what do you think homeostasis is?
Balance.
Yeah, it's balance. It's very much it's balance. It's a state at which your body is at, let's say, a neutral state, right? There are constantly bunch of different things happening in your body all at once, and it's like the state where all the systems are running at a normal capacity. And what happens in your blood sugar is traditionally your body is constantly between, let's say, between 3 to 5 millimolar or millimoles per liter of blood sugar or glucose at each individual day.
Bro, you just threw out some chemistry 11 words.
A little bit of chemistry, yeah. A little bit of chemistry. So there's a certain concentration of sugar, of glucose, that's constantly in your body it doesn't really swing. It goes 3 to 5, and it's pretty much 3 to 5 for a lifetime. The problem, what happens is when it swings too low, you get what's called a high.
3 to 5. I think I know what that means. Sorry, blipping in and out, but like I guess for context, my nephew also has
Type 1.
diabetes.
Yeah.
Type 1, exactly. And Bruno's lab is going to save their life.
Let's see.
But yeah, he'll come to me and he'll be like, oh, I'm low, I'm at like 2, or I'm at 1, or I'm like, I'm high, I'm at like 23 or 16.
Yeah,
15.
well, that's crazy. 16
Yeah,
and 23
yeah.
is really high. Yeah, so really what happens, the biggest danger is when you're low. So let's say if you're below 3, let's say you're at 2 or 1. We call that hypoglycemic. And that can get really detrimental because you don't have enough sugar in your blood, any glucose in your blood. It's not really transporting this precious glucose to the brain, etc. So you can get severely epileptic, and because your brain's not getting enough nutrients, enough oxygen, whatever. So it's
Sorry, the blood sugar in the blood, it gives it energy. Is that it, or is there more? It gives it like.
it transports. So glucose, your brain needs glucose to survive, right?
Yes.
And your brain, it's constantly needing a steady supply of glucose. So at
Yep.
too low, then your brain is not getting it, and unfortunately, your brain is kind of really sensitive to too low blood glucose. It'll start using other forms of energy, which can get very acidic, and that causes really, really big problems like seizures, epilepsy, etc. When it's too high, it's less of a problem. So when it's too high, it's like your blood is almost saturated with sugar, with glucose. And the issues and effects among high blood glucose is really kind of more chronic, like down the line, like blindness is a big one. Really poor immune system function is another one. Heart disease, cardiovascular disease. But those are more like
Damn,
chronic.
you can have blindness from high blood sugar.
Blood sugar, that's right.
Yeah.
And chronic high blood sugar, not like
Yeah.
short term. So that's the big problem among type 1 diabetics is that they have really, really big issues later in life regarding if they have too much sugar in their blood, if they're hyperglycemic. Because what insulin does, it works to remove the sugar that's saturated in the blood and sends it to your tissues. So if you have chronic high blood sugar in your blood, that's where the more later down the line side effects and issues start to happen.
And so your lab is trying to develop a way in which they can be treated more safely in the long term.
Yeah, what we're trying to do is really mitigate even the need for insulin. So right now, what people do is they'll take insulin on a daily basis. They have to take a very amount of insulin before a meal or after a meal, etc. And that's just, one, it's really expensive. Two, like I said, 30% of people don't really respond super well to insulin.
Yeah, you said that. Is it because of the long-term effects? Is that what you meant?
Yeah, because of
Yeah.
long
Or is
term.
it like something else, like sleep and eating and?
It's a combination
Like-
of everything. It's like sleep and eating. It's
Okay.
like stress, like stress in your pancreas, your liver, etc. It's a bunch of things that play a role.
Right.
And I'm not super informed. I am a type 1 diabetes researcher, but I'm not super informed on, let's say, the individual effects that a person has regarding if this particular amount of insulin is bad for them, etc. It's a very much like a individual basis in terms of how they respond to taking insulin. But in general, what we're trying to do is find a way to prevent even the need for insulin. So let's kind of take a small step back, and I know you're gonna have some questions about this as well.
Yeah. How is that possible?
So let's take a quick step back and think about, you have a nephew who is type 1 diabetic.
Yeah.
Do you know really how type 1 diabetes happens?
type 1 is genetic, so I've been told. Or it happens under extreme stress sometimes. And then I've been told that type 2 happens because of the maybe your diet.
Yeah, so let's flip everything all on its head. Okay. Let me give you a hypothetical. Let's say you had twins. Let's say you had a twin. And let's say one of your twins had type 1. Let's say your twin had type 1. What would you think is a likelihood of you getting type 1? Identical twin.
Oh, like 80%?
Because you think it's genetic.
Yeah.
Let's talk about
And
type
we're
2.
identical.
Let's say if you have
Okay.
type 2, what's the likelihood of your twin also having type 2?
Like 30, 40%? 40%?
Yeah. Okay. So that's what you think. It's actually, you have a higher probability of getting type 2 if your twin has type 2 than you getting type 1 if you have type 1, if they have type 1.
Is it still highly probable if my twin has type 1?
Yeah. I think it's closer to around, I want to say 30 or 40%. Maybe a little bit lower, actually. Maybe it might 50%. Type 2 is something around like 60 or 70%, if I remember correctly. But it's actually, if you think about that, it seems like type 2 is a little bit more genetic, which it can be. But let's think about, is type 1 diabetes a genetic disorder? We think it's linked to genetic disorder, but it's more so how I picture type 1 is like the Titanic. There is a lot of things that need to happen for you to get type 1 diabetes, even if you're genetically disposable to type 1 diabetes.
Okay.
So let's say like the Titanic, it was the unsinkable ship, right? What happened with Titanic was you had multiple compartments of the Titanic get flooded with water due to the impact of the iceberg. Similarly to type 1 diabetes, you have multiple compartments that need to be affected for you to get type 1 diabetes.
Yeah.
Okay?
Yes. Is that the main part of that analogy? Because like the Titanic, the main part of the Titanic going down is it hit an iceberg.
Which I don't know if it's like that.
There's a link.
That's the genetic thing. Okay.
Yeah. So that's actually not the genetic thing.
Okay.
The genetic thing would be the Titanic. The iceberg would be some sort of environmental factor that caused the Titanic to have a hole. It caused you
like a main catalyst.
Yeah,
in a sense?
like a trigger.
Okay.
So
Word.
there's a genetic component for sure. Let's say your immune system is a little bit more predisposed to attacking the cells that are producing insulin. We call those beta cells. Yes, so your immune system is a little bit predisposed already. It's kind of like a little bit primed that if like there's a trigger, the cells will indeed go in and attack the beta cells. But we think that the big environmental factor could be things like what you said, potentially beta cell stress or stress in general. Or let's say healthy, a poor diet, poor sleep, etc. Anything that causes some sort of stress in the beta cells. Maybe some sort of metabolic issue, like your beta cells have something going on with their capacity to regulate their own blood sugar, their own glucose. But the biggest kind of culprit, let's say, is some sort of a virus. Yeah, so that's the interesting one.
Wow.
So there is.
guess-
Wait, I raised my eyebrows, and I think you know why I raised my eyebrows. But in case there's more context to be had with that. Do you know why I raised my eyebrows?
Some issue with
Bruno?
vaccination.
No, well, I don't know. Bruno mentioned that you were saying a virus could be a trigger. My nephew got his diagnosis for type 1 diabetes circa 2020. So I think that's enough said.
No, let's not talk about COVID. It's
No,
not. I don't. I wouldn't say COVID. I don't
but I
think.
think
Not that it was COVID, but there were many things related to COVID that like could have caused a catalyst.
Potentially, I think I'm not because COVID is a more respiratory disease. It's not really like a intestinal
word.
or whatever. But but like I said, there's multiple things that kind of need to happen for your beta cells to finally be like, I can't do this anymore. You know, I'm all stressed. I can't potentially compensate for this.
Yeah.
And the virus that we're thinking of that's the biggest culprit, we think, not confirmed, but we think, is this virus called Coxsackie B virus. And traditionally, Coxsackie B virus is an intestinal virus. It affects your intestines. But for whatever reason, in some people, this virus is capable of actually infiltrating the pancreas and affecting the beta cells in the pancreas. Even though traditionally it's mostly intestinal. We don't know what that link looks like yet. But we think that like your beta cells are already quite stressed from being genetically disposed to type 1 diabetes. Your immune system is primed and ready to kill beta cells. It just needs to find a way to get in there. And then you have this virus that provides the perfect scenario for your immune cells, your regular immune cells, to come in and find the beta cells and kill the beta cells, as well as killing the virus-infected cells. So that's kind of the big thing that we think is happening with type 1 diabetes. So what happens is once you get this kind of multi-compartment failure, your beta cells will rapidly decline in number. Therefore, you don't have cells anymore that will produce insulin, making you need to take insulin through other means.
Yes.
Okay? So there's a lot more complexity towards this, but that's the long short of how type 1 diabetes is developed.
Okay.
Okay? So we're talking about insulin. We talked about how type 1 diabetes forms. We know that people who have type 1 diabetes don't really have properly functioning beta cells. So what I'm trying to do with my project is let's try to replace those beta cells. Let's try to give individuals with type 1 diabetes more beta cells.
Is that kind of like how insulin started? Didn't it like come from a pig or something? And we were giving this. Sorry, this might be like really abstract, long shot thought, but like, okay. Insulin they were trying to, there's people like, okay, they don't have enough insulin. Let's try to bring insulin in from other parts. And they tried to bring it in from other creatures. It got rejected a few times. And then eventually it worked.
That's very close to what happened. So
okay. And then is that what they're trying to do now with beta cells?
Well, what I'm trying to do.
Yes.
Similar. So
okay.
Let's talk about if we're talking about the history of how that happened. So the history of what we call beta cell transplantation, okay? That's what we're trying to do, is transplant new beta cells to a person. That way they have new beta cells to use. They don't have to take insulin anymore. So what happened is, what you're referring to is way back, more than 100 years ago, they were trying to replace beta cells in a person with type 1 diabetes. This is before even the discovery of insulin, okay? But they knew there was something going on with the pancreas. And what they tried to do was they tried to infuse, so they took like sheep pancreases, they minced up the sheep pancreas, and they infused the mixed up sheep pancreas through the blood into a boy with type 1 diabetes. He immediately died.
Yeah.
Obviously, a bad idea. But that's
What
like,
an idea.
but an idea, right?
Yeah.
So when insulin was discovered by Frederick Banting and Charles Best, two Canadian researchers, I believe they won a
Hey.
Nobel Prize, they discovered insulin. They found that insulin was important for beta cell function, et cetera, important for glucose function, everything. But what I'm trying to do is similar to what way back what they were doing is instead of course using a sheep pancreas, we're trying to transplant beta cells from stem cells. We're trying to basically recreate the pancreas from a stem cell and then transplanting those into a person with type 1 diabetes. Therefore, that person no longer needs to take exogenous insulin and they're good to go.
And just to recap, stem cells are like the fundamental parts of like cells and DNA.
Cells in general. So,
and they help you construct new things.
yeah, so stem cells are a cell type that can become any other cell type. That's the very basic
Right.
definition of
Yeah.
a stem cell.
I remember you saying that.
Your body that you have right now, when it was an embryo, early embryo, it came from a stem cell, right? From one stem cell that became another cell type, that further kind of became a little bit more specialized to becoming the individual cells of your body, the immune cells of your body, the blood cells of your body, the eye cells, everything, hair cells, everything. So what we're trying to do is recreate the pancreas from stem cells and then transplant those into an individual with type 1 diabetes.
I made an analogy in my head that feels a little ridiculous, but I think it's like Minecraft, where you have a piece of wood, and then you break that wood into either sticks or like other pieces of wood, and then the wood gets more specific to the specific tool that you need later on.
Exactly.
Okay.
Yeah.
So great. Those are stem cells.
Those are stem cells.
Yeah.
And so the question now that someone could ask is, why stem cells? Why can't you just do like a regular transplant from a donor, like an organ donor, and then transplant an organ donor's pancreas into a person with type 1 diabetes?
The body rejects things that is not theirs, right?
That's true.
Which makes me wonder how
organ transplants work, because I've never actually questioned that. How do organ transplants even work?
How do they work? Is through a lot of immunosuppressive drugs.
Oh,
okay.
Yeah. What organ transplants are to do, and what most people try. So pancreas transplants do happen from an organ donor. They definitely do happen. There's this protocol called the Edmonton Protocol. It's very famous now. It was in Edmonton, and they work a lot on isolating beta cells from an organ donor and then transplanting those into someone with type 1 diabetes who cannot regulate insulin. Like when they take insulin, they can't regulate blood sugar, so it's kind of like a last ditch effort.
Wait, so they actually are transplanting pancreases? Is that what you just?
Yeah,
Didn't
yeah,
say
it's
that.
very much a thing. It's been a thing for a while now.
What?
Yeah, they either transplant a whole pancreas or pancreatic beta cells, like the individual beta cells. That definitely.
And then they're
happens.
cured from diabetes forever?
Not necessarily.
pancreas.
So, like we said, rejection happens, right?
Yeah.
And typically, within about 3 to 5 years, they're gonna have to start taking insulin once again. Because your body's rejecting those transplanted cells. But it won't reject all of it. It will reject some of it for sure. But hopefully what happens is these are people who insulin does not work for them. They take this transplant because insulin will not work. So the hope is that by taking these pancreatic cells from an organ donor, they will take they'll take, let's say, insulin still, but it'll be kind of like the transplanted cells will provide some insulin and then, or enough insulin, and then they just take other forms of insulin too, and then they have like a little bit of a better response to sugar.
Right.
Right. So that happens. So rejection does happen, unfortunately. Unfortunately, it requires for this Edmonton protocol, which I mentioned, which just takes the beta cells, actually islet cells. I'm not going to talk too much about islet cells. Typically, you require 3 to 4 donors for one person.
Wow.
That's how much is needed for one person who receives a transplant.
Humans are not
very easy resources to come
No.
across ethically.
Unfortunately, no. So that's one thing. Some people have tried doing like beta cells from pigs, but then you have not just rejection from different humans, you have rejection from different species, which is an even bigger form of rejection than just between humans, which is even more dangerous potentially, but it definitely happens. But what we're trying to do is find a world, let's say have a world where potentially you have like precision medicine, right? You can take, let's say your nephew has type 1 diabetes. We can take the stem cells from your nephew, make them into a brand new pancreas, and then transplant that into your nephew. That way you have no rejection due to difference in humans. And then they can live on nicely and freely, hopefully without type 1 diabetes.
I have to check if I heard that right. So you're taking the stem cells from my nephew and then
Did you say editing them?
No, yeah, we'd have to do some sort of editing because we want to cloak them from your immune system, from your nephew's immune system. Because let's say if we take the stem cells, make them into beta cells, your nephew's immune system is just going to find those beta cells again and reject them and kill them, because that's how he got type 1 diabetes in the first place.
So we're putting immune suppressors into the ones that you've edited.
Yeah, we're cloaking them from the immune system. We're removing the capacity of your immune cells to attack those beta cells.
Is that dangerous?
Yes. Why do you think it's dangerous?
well, because what if something goes wrong with the beta cells that you just made?
Like, what if you get cancer, right?
Yeah, huge.
That is definitely a danger, absolutely. But the thing that most people try to do, or what the people are trying to do, is not putting the beta cells specifically back in the pancreas. We can just make beta cells and then put them in some sort of a device, like we call this a microfluidics device, and then implant them just under the skin. And then you can monitor these cells very easily every year, every month, 6 months, whatever, see if they're becoming cancerous or not, and then remove the transplant if there's a potential problem with cancer.
This is the idea for the finished product, or something that you're testing at the moment?
That would be the idea of the finished product. But
and that would just test if it is a procedure that you can do.
No, but I mean, I'm super far away from that, right? Those are big companies that are doing this microfluidics devices, this chip, organ on a chip, that's what they call them. There's this beautiful clinical trial led by a couple companies in the United States by Vertex. There's a whole documentary on it as well, a big, beautiful movie, that they're doing this exactly. They actually took stem cell-derived beta cells, and they put them on a chip, like a microfluidics chip, transplanted it just under the skin of a patient, and he has been insulin-free for the past, I think, 2 years now.
Right.
It's a really great thing.
But you need to know if this works for the masses.
For the masses, yeah. And
basically,
it was very much like a very kind of not preliminary because it's a clinical trial, but it's very much like there's a lot of room to improve on the clinical trials that are going on right now. A lot of room. It's quite early days.
So one of my earlier questions that was going to come up was one, what is genetic engineering? But we kind of touched on that. And how do we know if it's safe? And this is kind of your procedure to tell whether it is safe or not.
Yeah,
Is that
in
what
a
it-
way, to check if it's safe is you have this chip that if you transplant just under the skin, you can do a lot of diagnostics, right? You can visualize, see how things are going. It's a lot easier to monitor than, let's say, just putting your way back into your pancreas, where if you do that, there's just no chance that you're gonna be able to monitor it very well. Of course, the on the chip, you won't get like as good of, let's say, circulation of the blood as you would internally. But it's still, hopefully, it's kind of become more safety precaution. There are also things like, and this is where we can talk about genetic engineering, which I think is super, super interesting in my opinion, is called a kill switch.
Ooh, you can kill the cells you made?
Yeah.
Like in a movie?
So you could, in theory, and we think that in the future this is definitely going to happen, is you could genetically engineer these beta cells with a kill switch where if it starts becoming malignant, if it starts becoming cancerous, you'll kill the cells. Like,
Okay, that's cool. How?
how? Yeah.
Like, do you like put something in the body and it sends a signal to the beta cells that it's like, oh, it's time to die? Or, and I mean, like, can that go wrong? Because they have to be cloaked in the first place.
Right. So
You gotta kill something stealthy.
yeah, it's a super interesting thing, right? So death in cells is a good thing. All cells need to die eventually, right? If a cell doesn't die, it can become cancerous, right? So
You're preaching life lessons right now.
yeah, beta cells are really interesting cells because a beta cell is not like just like a regular skin cell or whatever. Beta cells are super what we call plastic. And plasticity is a word that's commonly used in science to refer to something that can be like molded in different shapes and sizes, etc. A beta cell can actually become another cell type in your body. It can become an alpha cell, which secretes glucagon, for example. It can become a delta cell, secretes somatostatin. It can become a bunch of different cell types in your body through a process called transdifferentiation. I'm not going to go too much deep into what. That's just the terminology for it. Beta cells are also very much known to do what's called de-differentiation. Remember how I told you that a stem cell becomes slowly more and more and more specialized until it becomes the cell type that you want. And there are very much steps to get to that specialization. It'll become this step first, that step next, that step next, that step next, etc., until it becomes the final product. A beta cell has a capacity to reverse course, to actually go back and become the earlier stage, like go back in that pathway. And the further it goes back, the worse the potential outcome.
Is this something that's unique to beta cells?
Not just necessarily unique to beta cells, but beta cells are definitely a big cell type that does that.
And relevant, I would assume.
And relevant. So that's the problem with
case.
That's the potential problem with cancer, right? Is if you have this beta cell that's nicely specialized, it de-differentiates. It goes back the pathway, becomes less and less specialized. It can become another cell type that can become malignant and become a problem, right?
And then cancer spreads.
And then the cancer spreads. We call this teratomas. Okay? A teratoma.
Spreads terror across the body.
No, it's probably one of the ugliest things you can think of. If you look up on Google teratoma, if you want to share your screen for the audience.
You know what? I was looking at that possibility and I've lost the possibility, so I'll just pull it up and edit. Here it is. There it is. I'll look it up on my own.
Yeah. Look up teratoma.
Oh, gross. I just looked at the definition. That's disgusting. It says a tumor composed of tissues not normally present at the site being typically in the gonads.
Look at some images.
Yeah, man. They're all censored.
Okay, so a lot of teratomas. So teratomas are, they have, let's say, like the definition. It's like a tumor that is composed of cells that are not supposed to be there. A lot of teratomas have, let's say, random hair poking out of it. Sometimes teeth. Yeah.
I found pictures.
So that's kind of what happens when, let's say, a beta cell becomes less and less specialized. Like it'll reverse course, become less specialized, and it's specialized into something else, like a tooth or like a hair cell or whatever.
I'm looking at something that looks like plasma mixed with teeth, mixed with hair, mixed with a toe.
Yeah, stuff like that. So that's a
That's
problem.
messed up.
That is actual nightmare fuel, right?
It's nightmare fuel. It's big nightmare fuel. And the problem is it happens. I'm doing a lot of work with mice, and one of my mice got a teratoma. And I do a lot of my test transplantations into the eye of a mouse because you can easily visualize it in the eye due to the fact that it's super clear. And I had a moment where one of my mice had this bulging mass of random crap coming out of its eye, and it was the most disgusting thing I've probably ever seen. So that's the problem with beta cells. They become more de-differentiated and they specialize into something else, becomes tumor, becomes malignant, becomes a big problem. So we can put a kill switch on these beta cells where if it starts becoming less specialized, we can find that. We know that it'll upregulate certain proteins. Certain proteins will get activated due to the fact that it's less specialized. And then it undergoes a process called apoptosis, which is just cell death. We turn on, let's say, a death program on the switch, on the cell. Like we switch on a death program, and then it just dies.
Okay, what? I think I have 3 questions, and I hope I remember them all. 1, you can just switch cells from the outside. I don't know if I heard that right. And dang. That was the only one I remembered.
Yeah, we can, because like I said, all cells need to die at some point, right? And cells have a way of knowing that it's close to death, and it'll turn on a program in itself to die. It's called apoptosis, is what it's called.
Oh, I see. And you can just... How do you turn that on? Because you're not at a computer being like, all right, everyone die now.
No, but we can put logic gating on a cell. We can put in AND gating or OR gating, just like in computer science, you do programming language. You can put in, if this protein is turned on, we can actually tether that to a death protein. And then if that protein is turned on, the death protein will also turn on and the cell will die.
So how do you know that that's only going to happen to the stem, the cells that you have engineered? Because part of me is assuming that, I think this is my previous question, that stem cells and native cells, I guess they're called, I'm not really sure. No, not stem cells, engineered cells and native cells will eventually what's a way to put this? I'm interlocking my fingers. They convert each other, I guess, and become one in a sense.
No.
And so eventually over time you lose which ones were engineered and which ones were...
Not necessarily, because remember, a person doesn't really have those beta cells, and these cells are very much isolated into this organ on a chip, right? So the cells that are there are homogeneously the cells that you transplanted them into.
So there's never going to be a case of information will leak out to other cells.
No, because
I guess that are native to the body.
No, because these beta cells would have been engineered genetically in their own DNA. So there's no leakage of their DNA, for example, that a cell will randomly take up this DNA and then have this kill switch on the other cell. No, it's very much tethered to the beta cell itself.
Okay. I feel like I've hit my limit of how much I know about biology on that one, so I'm gonna accept that as the answer.
Yeah, so the kill switch idea is really cool. I think it definitely is an interesting potential there. And so let's kind of keep chugging along here because I don't want to focus too much on this the intricacy of this, but
Sure.
So we've talked a little bit about stem cells becoming beta cells. We've talked about this kind of organ on a chip service. But the big problem that's in the field right now is making beta cells from stem cells is notoriously difficult because no matter how much we're trying, unfortunately, these beta cells, they don't really work as well as, let's say, a natural human beta cell that is not from a stem cell, like so just like the beta cell that you have in your own body, for example. Unfortunately, these stem cell derived beta cells, they don't work super well. Like they do work, but they're like not great.
Yeah.
And what I'm trying to do specifically for my project is try to improve the overall process of making these beta cells, like improve the functionality of these beta cells.
By work and not work, do you mean their ability to like sustain themselves inside the body or to produce insulin for the host?
Both.
Okay.
One is survival. They don't really survive very well. And two is their capacity to produce insulin in response to glucose.
Right.
So unfortunately, we're at a stage in the world right now where even these clinical trials that are going on, they do work, but they don't work super well. So what I'm trying to do is improve both the function and the survival of these stem cell beta cells.
Are you allowed to talk about your methods, or is that how like you know how do you have to be careful that your information doesn't get leaked into another lab?
Yeah, especially because my project has a lot of competition with other labs as well, unfortunately. So I'm not allowed to go out.
Yeah.
What's the likelihood that it's going to get out there from this podcast? It's probably not big, considering I presented a lot of this stuff in conferences as well. So I can talk about what I presented in conferences.
Yeah.
And super side tangent question, is tuberculosis like not being researched that much?
It is.
Okay, that was just a random thought I had. This from random videos.
We only really have another 10-ish minutes to go.
Okay, how would you like to proceed?
Maximum 15 minutes.
Yeah.
Did you want to dive a little bit deeper in that, or do you want to switch over to something else? Is there any lingering questions that you have?
I mean, dive deeper into what part? Sorry.
Specifically what I'm doing.
Yeah, let's do that. Because I know if anyone, my brothers will gonna want to hear this.
All right, cool. So I'll try to keep it brief. Long story short, we don't really know how a beta cell is formed naturally in the body, in the human body. We have ideas from a lot of work with mice, but the problem is fundamentally mouse beta cells or rodent beta cells are very different from human beta cells.
That's normal, right?
It's normal, but
humans are different things.
Yeah, it's normal, but it's particularly frustrating for beta cells.
Okay.
Yeah. Like mouse beta cells, they process glucose differently. They have different pathways of insulin secretion, like not insulin, different pathways of glucose response, of insulin response. So that's the big problem right there. And we can glean a lot of information from mouse beta cells, but unfortunately we can't get to too much. And the current method of generating stem cell-derived beta cells is based off mouse beta cell development. And unfortunately, in beta cell development, there is a lot of interactions with other cells that are required to help a beta cell become a functional beta cell. It's not just like one stem cell that becomes a beta cell. It's like a stem cell that becomes what's called a pancreatic islet cell, which is like the compartment of your pancreas that contains beta cells among other cell types. And that interaction of the other cells in that compartment is necessary for a beta cell to function. Okay. So imagine like, let's say, I don't know. Let's say you have, let's say in music, and let's say in an orchestra. A beautiful orchestra consists of all the different instruments that are working in unison to produce the sound that you want to make, the music they want to make.
Yes. Yeah.
Much like a beta cell, much like, let's say I'm an orchestra, a beta cell is one instrument in the big symphony.
Yeah.
Okay.
Cool.
It requires interactions with other cell types in that little compartment that holds the beta cells. It requires that interaction with the other cell types. We call this paracrine interactions. That to generate this nice functioning orchestra, of insulin. Right? So unfortunately, the problem that's going on right now is a lot of the methods to make stem cell-derived beta cells, they just focus on the beta cell. They don't focus on the other cell types that are needed. Because it's really complicated.
Oh, you gotta work with the whole orchestra is what you're saying.
You gotta work with the whole orchestra.
Damn. Okay.
Yeah, and that's kind of what I'm trying to do, is trying to piece together some other...
That's a lot of work.
It's a lot of work. And I'm not trying to piece together the whole orchestra all at once. Remember, science moves very slowly. So what I'm trying to do is introduce one component of this orchestra into this overall process. There's other people in the lab are trying to do other components of the orchestra, and then eventually, if we have enough components in isolation, we can put it all together and hopefully create a beautiful symphony of insulin.
Then you have to have ensemble rehearsals. Like you can have individual studio practice.
You gotta do it all.
Yeah.
Yeah. So
but all right.
That's essentially what I'm trying to do. And what I'm trying to do is, because I'm an immunologist by heart, is we're trying to include the good parts of the immune system into this symphony.
Sorry, the audio clipped out on the specific thing that you were working on.
I'm looking at the immunology side of it. So.
Oh, okay. Cool.
We're trying to integrate the good parts of the immune system that are necessary for beta cell function into this symphony.
So what are other people working on then? I guess in that case, let's talk about that.
Yeah, I mean, I can talk about what I'm doing as well. I mean, it's stuff that I've presented in conferences, so it's not a big deal.
Yeah, I guess more in general, like you're doing immunology, somebody else is doing,
let's say, the nervous system, integrating the nervous system into the beta cell. Other people are doing, let's say, more the cardiovascular system, trying to increase the vasculature. Like all these other components that they're working on in isolation to eventually bring everything all together into one centralized orchestra and then use that as a therapy.
Yeah. Dang.
It's a lot of work.
It's a lot of work. It requires a lot of people.
That's exciting, though.
Yeah, it's super exciting.
Are you excited?
Yeah, of course, Sam. It's a great project. It's a great thing. I love immunology. I'm in immunology by heart, right? So the fact
I
that
love that
they
you say by heart, like it's like it lives inside you. I love
yeah
that. But I mean, it's you're an immunology by certification, but you're
yeah
also taking it by
um
heart.
so I love the immune system. I love the fact the immune system is not just needed for fighting off infections. The immune system is possibly, I'm a little bit biased, but possibly one of the most important systems that your body has, not just for fighting off infection, but for actual development of the body.
Mm.
There's one
Do you think
sometimes.
a neuroscientist would disagree with you?
I think potentially. I think everybody has their own biases. Human beings are biased by trade, right? Um, but definitely the immune system, let's say specifically a cell type called a macrophage, which is what I work on.
Yeah.
It's needed for proper development of a bunch of cell types in your body, like proper functioning for a bunch of cell types in your body, including beta cells.
Right.
So what I'm trying to do is integrate these macrophages into this whole beta cell specialization process at the right stage of their specialization, at the right amount of cells, at the right amount of time, et cetera, et cetera, et cetera, and then try to at least solve one potential component of this symphony. I'm pairing up with the violinists,
I no, that confused me more than anything.
yeah. That's what I'm working on. Which involves a lot of engineering, a lot of genetic engineering, which I think at some we can probably touch on at some other podcasts. But
yeah, I wish we could dive more into macrophages because I realized this whole time that I thought beta cells were macrophages. We've talked a little bit about this, and every time I probably have a little glazed look over my face. I'm just like, oh, okay. And the whole concepts of beta cells and macrophages have intertwined themselves as the same thing.
yeah, so beta cells are not macrophages, that's for sure.
Yes. And now I want to hear about what you're doing with macrophages. Macrophages? Not micro.
Not micro.
Macro.
Yeah. But I fear that we've hit our time.
Let me just double check my let me take a quick 2-minute break. Let me just double check my transit and everything.
Bro, this teratoma looks gross.
Yeah, it's not
It's
great.
still sitting on my screen. It's the sickest thing I've ever seen in my life.
I feel like I'm looking at like an appropriate one. That is like that is an actual nightmare.
Yeah, it's definitely nightmare fuel. That's for sure.
People like directors have used this for like horror scenes.
Yep.
Bruno had to check his little schedules very quickly, and he is right out of time. But thank you so much for joining, participating, listening, viewing. And thanks, Bruno, for explaining complicated, or maybe not complicated, biology things to me with someone who has absolutely no biology experience. The things that you talked about today did make me want to, like, I wrote them down, things I wanted to ask, but didn't because I want you to like finish thoughts. I know I interrupted you a lot, but I also did. I want to know what you think about animal testing for one, because I know that's a controversial topic, and that's something that you have a lot of thoughts on, as well as ethical testing related in such a way. But you also mentioned the organ chip, which I was wondering, is that related to allergy testing? So these are things that we may talk about on the next stream, on the next podcast, or we might not. We might just pick something completely separate. Do you have any final words?
No, I think I'm very happy to explain what I can explain, and hopefully it's not too boring, because I think a lot of PhDs and science can get quite a bit boring for a lot of people. But
It's hard. I mean, I have the same thing with music. It's hard to know where the jargon started and where it's like simple. And I don't know if I'm like being condescending sometimes when I'm explaining something.
But I think there's a lot of people that say the best scientists are the ones that know their stuff so well that they're able to explain it to a 5-year-old.
Yes.
And I think that goes with anything, and I think that's a really important thing for a lot of people who go into careers in science or in music, or I'm guessing music as well, but or in anything in math, is not to overcomplicate things, and it really helps talking to people who don't really know your topic, because it really forces you to, boil it down into concise paragraphs. So
Yeah.
Very happy to do this.
Yeah, thanks, man. We love it.
Awesome.
All right, fare thee well. I don't know how to do a send off.
Thanks for joining.
Yeah.
Hopefully it wasn't too boring, and hopefully it was exciting enough amidst all the technical difficulties. And we're looking forward to talking about something else next time. Hopefully it'll be good.
Until next time. Bye.